afternoon, everyone. Sorry that this might be interfering with lunch. I think that's probably one reason we don't have the full attendance right now. But Avicena, so most of you probably haven't heard of us, even though the company was founded 2 years ago. We do have good genes. So the founder and the brain behind this whole technology is Bardia Pezeshki. So some of you probably know him, Santur, Tunable Lasers, founder of Santur, founder of Kayam. This is Avicena, third time's a charm, as they say. I'm going to spend some time of talking about why. Why is this interesting? Why is it relevant? Before we get into the what and how exactly we do. And I'm going to start with this slide here. This is a picture from the keynote speech from IAA. This is the automotive show in Munich of last week. And this is Pat Gelsinger. For those who don't recognize him, he's the new CEO of Intel. And I mean, what we're doing here is, if you're not famous yourself as a company yet, then you ride the coattails of the big guys. But actually, it's two reasons. One reason is just to illustrate how chip-to-chip interconnects are going everywhere now. This is in automotive. I mean, cars, everyone drives a car. They're turning into computers on wheels. But the other reason I'm showing this slide is those four components of the digital world. And I'd like to point out the second one from the left, so the connectivity, because that's where we as optics guys usually spend our lives. Connectivity, and when we think connectivity, we think big networks, we think long distance. Okay, it's gotten shorter now down to a few hundred meters, but we don't think centimeters or a few meters when we think connectivity. And that's where the first bucket comes in. In computing, computers are turning from individual shelves into clusters of processors and memory. And all these different elements need to be connected. So that's where interconnects are going to. And that's where the current approach to things is running out of steam. It's not working anymore doing this with electrical connections. So a lot of people in the computing industry, in the chip industry, are saying what Steve Wu is saying. There's a public statement by him. Data movement is the thing that's now limiting compute performance. It's no longer the processors. And there's mostly two reasons for that. One reason is, again, most of you have heard of Moore's Law. Moore's Law is running out of steam. It's not dead, but it is definitely what we had from, let's say, from the 80s through about 2000. We had a nice increment in processing performance for the same footprint, the same energy consumption, the same cost, by just using the manufacturing machine that the semiconductor industry entails. And that's been starting to level off because the dimensions are getting small enough now that you're starting to see quantum effects. It's not dead, but it's getting more and more complicated. The improvements, as you can see, is a few percents per year now, where it used to be 50% per year. So that's one reason that people are looking to increase performance by building clusters. And the other reason is a little more complicated, so please bear with me. I'll give you a quick tutorial for optical engineers on how compute networks work today and what changed over time. For those who know this, please bear with me. Apologize for lecturing you on something you already know, but it definitely took me a little bit to understand what's going on and why, again, interconnects are becoming so important. So on the left, you see a list of all the resources, and then on the right, you see what a traditional server used to look like. There always was a pair, just about every time there was a pair of CPUs, some memory on the server, then a network interface, a NIC, and possibly some storage offsite, and then the connectivity, starting with the NIC that went to whatever destination they're looking for. Now, as things have gotten more complicated, especially driven by AI, where it's no longer sequential computing, a lot of it is parallel computing. That's where GPUs came into the picture. This happened a few years ago, and it was the GPU to CPU to memory interaction that started to make the servers more complex. But still the basic same architecture, you do that in a server, fairly small size, you go through a NIC interface, you have access to some external storage, and you connect to the network. But what's now turning out, as we're getting deeper into machine learning, as we're doing all these training and then inference applications, there's actually no two workloads for computing are alike. And it was mentioned earlier by Mark in the AR Labs talk that as the workloads are different, in some cases you need a lot of memory, some workloads need a lot of processing, some workloads need yet something else. But if you have a rigid small building block of a compute server with a little bit of memory, a little bit of CPU, the usage of the different elements becomes very inefficient. When we're talking to NVIDIA, for instance, they're telling us the usage of memory that's in a standard server can be as low as 30%. Well, that's not efficient at all. If you can build a bigger cluster, you can bring that usage up to about 80%. It's never 100%, but it's a factor 2 or 3 better. But again, in order to do that, you need to be able to move your data rapidly between the processors and your various memory locations. And that's basically where we are now. So this is a modern disaggregated cloud server. This one happens to be the DGX from NVIDIA. So what you recognize is still the same basic structure at the top, just more memory. But then now you have a whole cluster of GPUs. They can go up to 8 GPUs. They manage to fit all that on one PCB. And they're connected through. Now, NVLink is, if you like, the NVIDIA proprietary equivalent of a PCIe CXL link, which is very ubiquitous in the server world. They can connect up to 8 GPUs. They can add another PCB with another 8 GPUs. That would then make up 16, and they can still all do that with copper. It's not particularly effective, but that's what they have to do today. But they're telling us if we had a low power link that could get us a few meters, we don't really care whether it's optics or electronics. If we have that link and hasn't worked as an electrical link, and I'll show you why it's unlikely to ever work. But if they had that, they say they could cluster up to 100 GPUs. That's what they would like to do. So it's a burning need. They're basically stuck with the current technology on doing this. Yeah, so there's a statement that we had from Bill Daly, for those who know him, is the chief scientist of NVIDIA, that was saying, well, what you're developing here at Avicena with these LED-based links, that's very promising. Now let's just keep exploring the whole link paradigm a little more. What's important for any communication link? So we've listed 4 things, there's probably more, but those are 4 key elements. You always look at the bandwidth, obviously more is better. But the new thing that's everyone talks about is the beachfront density. I mean, we've heard that term now. It's, if you like, it's kind of the new normal, what used to be called faceplate density. We've known that in the optical industry for quite a while. Now we're talking about beachfront, and that means how much room at the edge of a chip do I need to take up to move a terabit? And sort of the currency there is typically between 1 and 2 terabits per millimeter of chip edge. You can also then look at how much real estate do I take up, but let's just keep it linear for the moment. And then you want this low energy. And low energy, I mean, in the optical world, traditionally in networking, we've crossed the 10 picojoule per bit line, the cutoff on the way down. So we're getting below that. AR Labs was showing they think they can get to 5 picojoules per bit. I don't think they're quite there yet, but that's what they think they will achieve. We can show you in our projections that in an LED-based technology, you can probably get to about 0.1 picojoule. So another order of magnitude below a picojoule. And then you want low latency, nanoseconds if possible. Now there are two things that you need to know about LEDs. They're all, and I'm going to say that more than once, they're all relatively low data rates. Now, historically, micro LEDs that are used in displays, they just need to keep up with the frame rate. So it's a few hundred megabits per second. That's really all you need. We've managed to modify them so that you can transmit up to 10 gigabits per second on a single LED. And we actually have we have a booth here, we have a demo. It's number 916, so please stop by. We'll be happy to show you that. As far as we know, this is the world record in data rates for LEDs. I think the fastest LEDs have been running up to about a year ago were on the order of 1 gigabits. That's what other people have shown. That, no, it could be something somewhere in a lab, but we can show you 10 gigabits. And the other thing is because their LEDs are not lasers, so they don't need to come above threshold, so they're much lower energy. We can run them, we're also showing that, we can run that at microamps rather than milliamps to get communication. Now the trade-off is you cannot go further than about 10 meters because you just don't have enough power. Okay. This is the chart that a lot of people have seen now when we compare kind of the figure of merit of an optical link. It was, as far as we know, it originally comes from DARPA. Dr. Gordon Keeler has shown that to compare things. Let me walk you through it. So what you see across the bottom on the x-axis is the distance. Now this is going, so you got 1 meter right there, sort of slightly to the right. So this is extremely short here on the left-hand side. And then it goes out to about 100 meters. So it's not 100% fair to silicon photonics, because silicon photonics or optical technologies, they can usually go about 2 kilometers or more. If you're talking coherent, obviously then it's much more. So keep that in mind as well. But you can now see where these electrical links that people are using for computer clusters, where they are. It's the orange line and all the different examples of electrical links pointed out on the left. Then, so this is state of the art. This is there today. And then on further down on the right, so starting at 1 meter, you can see what optical can achieve today in terms of discrete components. And in some cases, you actually see the famous optical backplane that I remember we were talking when I was at Pirelli WDM Systems over 20 years ago. We were talking and trialing optical backplanes, never really caught on, because you can see you're not really gaining anything compared to electronics. You're sort of in the same range. It's more complicated. Connectors are always dirty. They're hard to get to when they're in the backplane. Never really caught on. Now, we have had a lot of talks on silicon photonics. So silicon photonics is promising to push the efficiency up, this figure of merit in terms of bandwidth density, and energy efficiency. And again, it extends further to the right. I know that there is claims that silicon photonics will eventually go up to the kind of the 10,000 level. I don't see this happening anytime soon. Never say never, but I don't see this happening anytime soon. With an LED link, so this is, we call our links the light bundles, you see where this stands. So it's a couple of orders of magnitude above kind of what we achieve today with silicon photonics, but it cuts off at 10 meters. So it's perfect for compute clusters. You're not going to get across a large data center. Just not going to happen. You don't have the reach. So that's why LED-based links are a big deal for anyone that is looking at computer networks. And since computer networks now exist in almost anything we buy or use, be it a smartphone, be it a car, lots of appliances, it is a big deal. And this is just the kind of another illustration. Again, this is now interconnect length, but it's a shorter. It's just we're just showing 20 millimeters here, and then this is just the energy per bit. But again, you can see up on top a traditional electrical interconnect, 50 ohms of standard interconnect. you're just stuck up there in terms of energy consumption. If you do that with kind of if you look at the electrical capacitance, you see this curve. So again, it becomes very low energy as you're getting very short. That's why chiplet interfaces, it was mentioned, for instance, an HBM interface clustered around the CPU, that works in electrical. But as soon as you need to go just a few millimeters, definitely as soon as you reach 1 centimeter, it starts to not work very well, and then it keeps degrading from there. And that's where if you take sort of an LED-based link, and of course in the optical world, the energy you need is the energy to generate the photons. Once you have photons generated, they travel virtually loss-free over short distances. Whereas every time you have a copper wire, you got resistance and capacitance that you have to overcome. You have to power the wire, so it's not a surprise that it is the way it is. By the way, for those who like to go deeper on the technology, we have a technical talk. Vardia will be giving a technical talk on Wednesday here at the conference, so I encourage you to go check that out because you'll get a lot more detail. But here is the kind of the artist's impression on what we do, how the light bundle, the key components of the light bundle. So we have these micro LEDs, those are the emitters, and of course you have to modify them so that they can run up to a 10 gigabit modulation rate, data rate. But they're still based on the micro LED technology from the display industry. That means the volume production is already in place. You just have to adjust it for this particular technology. They're grown separately on sapphire wafers, and then it's the material is gallium nitride, as all display LEDs are today. And they're small. They're kind of 10 micron square. They're on a grid. Today we use a grid of about 50 micron, but we think that can be shrunk. That can probably be about cut in half. You can then transfer them and bond them to any CMOS chip. So you can integrate the transmitter, if you like, onto any CMOS chip. Or you can have a separate chip and then a short reach chiplet to chiplet interface. Both options are possible. Then the light gets coupled. Depending on what you do, you can direct couple a fiber. That means you have a vertical exit, either up or down. Or if you want a horizontal exit, and for some applications that's preferred, you have a coupling optics with a 45-degree mirror, and then you couple into a multi-core fiber. And there are, again, this is technology that exists. You got the lighting industry that's using multi-core fibers. You got the imaging industry, endoscopy. Of course, we can't pay what we pay for medical equipment in the communication world, but the volumes are completely different. So that's why this is achievable. And the other thing is, since these are highly multi-mode applications here, your tolerances are actually comparable to multi-mode tolerances. It's not single-mode tolerances of sub-micron, which is always a challenge when you need to couple it, because you need to couple the entire array. And of course, there is some trickery needed to make sure that you can maintain your relationship between your transmit and your receive side. So you need to maintain the tolerance through a whole array, not just a single. But this is all doable. So you travel through your multi-core fiber, and then on the receive side, the light wavelength that we're talking about here is in the blue. It's about 420 nanometers. Well, 420 nanometers happens to get absorbed in silicon very well, so very short absorption length. So you can actually make your PDs, it's just in silicon, there's no germanium needed, just in silicon, so you can actually grow your PDs, your receiver, directly on a CMOS chip. So those are per se integrated. They're just grown onto your CMOS chip with a few extra steps. So it's very easy to integrate it with a chip, because that's one of the big challenges for most optical technologies. How do you integrate it with your chips. If you're thinking about every CPU, every GPU now has an optical or even multiple optical interfaces, you cannot have bulky optics interfaces. It's hard to have external lasers, but you need external lasers in most applications because lasers cannot take the temperature at which most of the ICs are running. That's another advantage of LEDs. ICs run at 80 to 100 degrees C. I mean, you saw AR Labs talk, 80 to 100 degree. That's why they moved the laser external. LEDs can go up to 125. We've actually done kind of lifetime testing up to 150 degrees C. They can take that. And again, it's known, the reliability behavior is well known because that's known from the display industry where stuff gets hot. And yes, I mean, so up here you have the pretty pictures. These are just a couple of examples on where we are right now. So we have these coupling optics, first samples. This is molded. And then we have some CMOS arrays here. Right now we did one. This is still relatively benign in terms of node. So it's a 130 nanometer node, and it's two 128 LED and PD arrays. Of course, there the performance is limited. It's not particularly energy efficient because of your 130 nanometer CMOS system. Most of you probably know what it costs to do a 5 nanometer CMOS mask right now. So as a startup, we can not quite afford that yet, but that's where this is heading, and you can obviously do it in that node system. Okay, so let's recap one more time on where the performance stands for this light bundle interconnect. High bandwidth density. So call it between 1 and 2 terabits per millimeter of your edge, chip edge size. Ultra low power, think 0.1 picojoules or 100 femtojoules per bit. Low latency, so the 5 nanoseconds here is called out for just the optical front end. So you'd have that on both ends, and then it's obviously the time of flight. But the modulation is NRZ. We don't need, because we're going at up no more than 10 gig. You can just do NRZ. Keep it simple. There's no PAM4. There's no conversion. Unless you have really special applications, you don't really need FEC. So you can keep the power down because all that adds to your power as you're doing that. We already talked about the maximum temperature. So you need to be able to, and in production they can go even higher because you need to be able to tolerate reflow temperatures when you build it. Reach, think 10 meters, up to 10 meters. So really the sweet spot from what we can tell, talking to all the interested parties, it's centimeters to 10 meters. Again, this was talked about a few times. I'm going to give you my view of the market. We have different segments. It's combined. It's a large market. This is sort of we see this north of 50 billion in terms of the addressable interconnect market by 2030. So call it 10 years out. Large market. Obviously, a huge need in the HPC cloud application. But there are sensors. We're already working with one of the large sensor companies that is looking to use this to connect a sensor with the processor. And if this goes into a smartphone, any wire that you can save in there helps you with your reception because any wire in a smartphone is an antenna. Picks up or picks up signal or interferes with other signals. Automotive. So there is actually I didn't know this, but there's a McKinsey study that projects by 2030, 20% of the BOM of any luxury car will be ICs. And they peg that number at about $115 billion. So that's for the IC. So if you just think 10% of that is your interconnect, there is your 10 billion right there. And then aerospace, Mark called this the intelligent edge. It's the same phased array devices, phased array radar, LiDAR, that kind of stuff is definitely another big application. Oh yeah, sorry, I actually had the chart here. This is the McKinsey study. That was also revealed last week at the IAA conference. And there is one more thing, again, if you look at the energy efficiency, it's actually becoming a big deal for humanity. I mean, our data centers they're popping up everywhere, and again, the projection is by 2030, data centers will consume somewhere 10% of the world's energy. So if we can save half of that by using a smarter interconnect, and it would be nice if that would be the optical community delivering the solution, we're all better off. I kind of want to leave you with that thought. We've seen a lot of blue, so this is some green here. So we're looking forward to that. And with this, I thank you for your attention. I'll be happy to take any questions.
Thank you. Yeah, we have one question.
Thank you, Christopher. Since you moved the company may have something, I'm sure. Then I have one question to your LED. 420 you mentioned, like a 420 nanometer, something like.
Sorry,
blue, 420.
Yes, nanometers.
Yeah, okay. So it's good for like silicon feed can detect everything could be good, but one question is like you show the core to core POC the cable, and I just wonder. I mean, if each core to core, each channel to channel, the uniformity would be a little bit different. I'm just curious about how can you manage the interconnect. Then must be similar the dB. I mean, similar milliwatt should be delivered, but in that case, core to core could be some kind of different power. So how can you manage it?
Yeah, so it's an excellent question, and obviously there's a range. It's something that needs to be managed, but we found that so far in our work we found that to be manageable. You also need to key your fiber cable so that you have the right PD paired up with the right LED, and in some applications you might need some equalization, but it doesn't look like it doesn't look like it's that critical. So it looks like that can be handled. Thank you.
Any other questions? So the one question I had was, it sort of relates, when you go multi-core fiber, is it one single per one optical signal per core, or can you have many per core?
That's an excellent question, and actually the answer is right now we're pursuing both. Because if you look in imaging fiber, you got thousands of cores and they're very small. That's one option, and then in the kind of lighting fiber or there you're looking at one LED per core, and then you just pull that. So the Optima hasn't found yet lots of opportunity to file IP in there, which we're busy doing. So I would say the winner hasn't been declared yet.
No, I had forgotten about the imaging fiber, which is basically a bunch of cores all clumped together. If you could get those aligned to the array, then that's a really interesting solution. Yeah, thank you.
Yeah, you're welcome.
Any other questions before some of us go for lunch? All right, let's thank Christoph again.